Deepa, can you hear me and see the screen? Deepa, can you hear me?
Yeah, I can.
Okay. Good morning. Hope you guys can hear me and see the screen. I'm going to wrap up our discussion about MOSFETs today and then jump into a discussion of bipolar junction transistors. Just to refresh your memory, where we ended up last week was with the discussion of short channel effects such as DIBL or drain-induced barrier lowering, which causes the output current ID to not saturate as a function of VD, but actually keep going up, as you can see in this hand sketch over here. And the physics of that essentially boils down to a two-dimensional electric field profile when you shorten the channel length, okay? And what we discussed was, if you initially consider a long channel device shown by this dotted line, the corresponding channel potential along the channel from the source to the drain end is shown by this dotted blue line. And you get a potential barrier between the source and the channel, which basically corresponds to the PN junction potential barrier over here. And that is what prevents the transistor from conducting, except for low PN junction leakage currents. But then if you apply a gate voltage, you can lower the potential barrier between the source to the channel. And if you lower it sufficiently by applying a voltage greater than the threshold voltage, you flow in carriers from the source and the drain into the channel, form an inversion layer, which then connects up the N plus source to the N plus drain, and the transistor turns on. In a well-designed transistor, you'd want that drain current to be controlled only by the input gate voltage and not by the drain voltage, which is the output voltage, because that would then reduce the output impedance by giving you a finite slope of IDBD, which is not something that you want, okay? Now, unfortunately, if you scale down the channel length, as shown by this solid line in the structure and the corresponding potential profile, what you find then is as you increase VD, the potential near the drain goes down because the electron energies are minus Q times VD. And as you keep doing that, look at this solid curve over here. At some point, the reduction of the drain voltage for a short channel device, increase of the drain voltage, or reduction of the drain potential energy for a short channel device leads to a reduction of the source to channel potential barrier. And that's why it's called drain-induced barrier lowering, okay? Now that's not something that you want, because if the drain now lowers the potential barrier, that could cause carriers to be injected from the source into the channel region more and more, and that's what causes this finite slope of the output characteristics, okay? Now, if you think about it, it's really based on two-dimensional electric field profiles, okay? Because now in this region, if you look at the depletion charges, some of the electric field lines terminate on the gate, which is what you want, but then some of the field lines terminate on the drain electrode, and that's what's responsible for this lowering of the potential barrier, okay? And that's kind of shown in this IDVD. So that's drain-induced barrier lowering with a finite slope. And like I said, that's not a desirable thing. Now, the additional sources for this finite output impedance that we have mentioned before, and one of them is the hot electron effects that you get in the pinch-off region. That generates additional electron hole pairs, and that also causes the output current to go up. Okay. And in fact, at some point, the current can go up catastrophically, leading to a breakdown of the transistor. The next topic that I'm covering is called charge sharing. And in some sense, the physics is reminiscent of this DIBL effect that you just talked about, okay? It's slightly different, but essentially it boils down to having to solve a two-dimensional Poisson equation near the ends of the channel region, okay? What I'm showing here is the depletion region for a low drain voltage, say, and that's shown by the solid line. And then you have a set of equipotential contours, one of which is shown by this dotted line. And you get, of course, a whole bunch of these equipotential contours, okay? Now, if you have equipotential contours like that, we know that the electric field, E, which is shown by these vectors over here, has to be perpendicular to the equipotential contours. We call them V equipotential, right? Because E is equal to minus dV dx, okay? Therefore, along these contours, the potential doesn't change. Therefore, minus dV dx has to be perpendicular to that, okay? And what you find is, in these regions, at the ends of the channel, highlighted by these blue triangles, as this equipotential contour curves around, the electric fields also curve around. So in this part, in the source drain, the electric field points vertically down. In the middle of the channel, the field lines terminate, are pointing vertically down from the gate into the depletion charges in the channel. Same over here in the drain, but near the ends of the channel, because of this two-dimensional equipotential contour profile, you find that the electric field lines curve around, as you can see visually, okay? Now, what is the impact of that? The impact is the following. If you look at the expression for the threshold voltage, we proved several times that is given by the flat band voltage, that is the gate voltage needed to cause zero band bending in the channel, plus twice the Fermi potential. Fermi potential is the difference between the Fermi level and the intrinsic level. And then finally, you had, in this case, depletion charge over Ci, the insulator capacitance, where depletion charge for N-channel device, where I have acceptors in the channel region, the depletion charge is minus Q Na times W, okay? This minus and this minus makes the final term positive. The important point to note is the VT depends on the depletion charges under the channel region, shown by this rectangular region of the depletion charge, okay? Because that's physically lying underneath the gate electrode of length L. However, because of these two-dimensional equipotential contours and this bending of these electric field lines near the ends, what you end up getting is a funny thing, and that is you have these depletion charges shown in these blue triangles, which physically lie underneath the gate electrode, but actually have their field lines terminate on the source and the drain, okay? And that's what I mean by this concept of charge sharing. These depletion charges, which physically lie under the gate, are actually being shared in the sense that the electric fields are terminating on the source and the drain. The upshot of this is the depletion charge term in the final term in the threshold voltage expression, instead of being QD, should be a lower value, say QD prime, where QD prime corresponds to this trapezoidal region, okay? So the only depletion charges that I should count in the final term are the charges whose field lines terminate on the gate, and you should exclude these blue triangular regions, okay? Well, if that's the case, what's going to happen to the threshold voltage? Obviously, the threshold voltage would be lower because of these triangular region depletion charges not counting towards the VT. Now, the thing is, if the channel length was very, very long, these blue triangular regions on a fractional basis don't really count for that much, right? So you have a so-called long channel threshold voltage. But as you reduce the channel length, because of this charge sharing becoming a larger and larger fraction of the total depletion charge under the gate electrode, that causes the VT to be lower, okay? Now notice the similarity in the physics with Dibble, but the difference is also, right? So as in Dibble, you have field lines which have these two-dimensional characteristic near the ends, but the physics is different. In the case of Dibble, that was caused by this drain voltage VD rising. In the case of charge sharing, it's because of these depletion charges having field lines terminating on the source and the drain. Now that turns out to be a problem in manufacturing, because in Cmos technology, you're always pushing the limits in terms of having as short of a channel length as possible. Because you've seen, if you have a short channel length, according to the Dennard scaling rules, you can scale, you can put in a whole bunch of transistors together on your chip. The transit time between the source and the drain is shorter, so you get faster transistors. It consumes lower power per transistor switching operation. Lots of good things happen, okay? The problem becomes, in manufacturing, you can never control the channel length precisely. And if you have variations of the channel length, that also corresponds to variations of the threshold voltage and other circuit parameters. A very analogous thing is shown in this other curve, which is called the narrow width effect, okay? So here, I'm looking at the transistor, not along the channel length. So in this case, the source and the drain, the channel direction is perpendicular to the plane of the board, okay? I'm flipping the picture here, and I'm looking at it from this direction, okay? The width direction. And suppose I make the width narrower and narrower, okay? So that's my channel width, which I've been calling Z in the textbook, but in the literature, often that's called W. We didn't call it W because we reserved W for the depletion width, and we didn't want to be confused, okay? But if you read many papers, people will more often than not use W for the channel width rather than Z. So what one finds is as you make this width narrower and narrower, you have depletion charges at the end shown in these blue triangles, which have these field lines terminating on the gate electrode. And for a very wide transistor, they don't matter that much. But for narrow devices, these are a larger and larger fraction. Okay. And what are these depletion charges due to? These are charges that physically lie outside of the gate electrode region under the field oxides. These are the isolation regions. Okay. So this is an example of what's called low-cost isolation. Okay, where you grow a local oxidation to have a very, very thick oxide. And the reason for having a thick oxide, if you remember, is if you have a very, very thick oxide, is expression for the VT, the CI, which is the dielectric constant of oxide divided by the thickness of the oxide, becomes very low. So if D, the thickness of the oxide goes up, CI goes down, so this final term goes up, and VT increases. And the way you get electrical isolation between, say, this transistor and maybe another transistor over here, another transistor on the right-hand side, is by making the VT in these regions very, very high, much higher than the power supply voltages. And that's why you have no electrical conduction between this transistor and neighboring transistors, right? Now, when you form these isolation regions, you can also have additional depletion charges that are implanted. That's called a channel stop implant. And that amounts to increasing the doping, Na, under these isolation regions. And then those depletion charges cause this narrow width effect. Now, this turns out to be, from a technology point of view, not as critical as the short channel effect, because since drain currents typically scale as width over length, and then you get all these other parameters, you generally want a high drain current. So typically the widths of transistors that you have in circuits are generally pretty large. So you'll be in this region in terms of the width, but the channel lengths are going to be very, very short. So you're operating in this region. So the short channel effect is very important. This one, not so much. In this figure, I'm showing you what's called an equivalent circuit of a MOSFET. Okay. The concept of an equivalent circuit we introduced very briefly when we talked about PN junction diodes, where we said that an ideal diode is like a digital device which conducts with infinite conductance in the forward direction and is in the off state in reverse bias. But in practice, of course, we saw that there's a finite cut-in voltage corresponding to the junction potential. Plus, you have you have series resistance in the P and the N region and all that. And then in the diode, you also have capacitors because of the depletion capacitance. So that's the kind of philosophy behind equivalent circuits of all semiconductor devices. Okay, so what one does is you solve the IV and the CV characteristics by solving drift diffusion equations or what have you. And then when I want to do circuit simulations, it turns out to be impractical to always solve the drift diffusion equation for, say the 3 billion transistors that you have in your Pentium microprocessor chip in your laptop, right? That's not practical. So instead, what's done is you capture as much of the physics as reasonable and needed for your particular circuit application in terms of lumped resistors or lumped capacitors and so on and so forth. Okay, and that's what's shown over here. Now, the more physics you want to capture, the more of these lumped resistor capacitor elements that you have to put in, okay? But this shows kind of some of the more important parameters, okay? The most important parameter is the one in the middle, which is gate voltage controlled current source, okay? So that's my current source. And the current is the drain current, ID, is given by the transconductance, GM, times VG, okay? Where the transconductance is delta ID over delta VG, okay? So that's really the most important part of the transistor, okay? But unfortunately, along with that current source, you have a whole bunch of these lumped resistors and capacitors, some of which are unavoidable. So for example, in the gate electrode region itself, you have the gate capacitance, which I'm showing in a distributed form to the channel, partly towards the source end of the channel and partly towards the drain end of the channel. So that's the one that we have been calling CI in the MOS equivalent circuit so far, right? So you got the gate electrode, you have the gate oxide, so that CI is shown in a more elaborate fashion as a distributed capacitor, okay? In the source and the drain regions, those are PN junctions, so you'll have depletion capacitances associated with those, okay? In the source and the drain regions, we will also have series resistances, RS and RD, and the two of them are very often lumped together as RSD, as the sum of RS plus RD, okay? I think I've hinted at this before. The issue is, if I apply a drain voltage VD, and there's a current ID flowing in the structure, there'll be a voltage drop ID times RSD across this RS plus RD, okay? And therefore, the voltage that's applied to the transistor itself, okay, that's the intrinsic part of the transistor, VD prime, would be the externally applied drain voltage, VD, minus ID times RSD. RSD is equal to this quantity over here. So it'll be VD, that's externally applied, minus ID times RSD, where RSD is equal to RS plus RD, okay? Of course, that's waste, right? So that means there's less voltage available to be applied across the intrinsic part of the transistor, and you get less drain current, okay? So essentially what it means is you want RSD, or RS plus RD, to be as small as possible. And we'll see in a second how that's achieved in practice. Now, there's other resistances also that are important from a circuit point of view, which is in the bulk. I'm not going to get into that because those are more advanced effects, things called Cmos latch up, where a Cmos circuit goes into a low impedance state between the power supply and ground, and your IC can basically burn up. If you take a graduate course, they'll talk about that. Now let's focus on the capacitances, okay? Now this part of the capacitance, of course, is unavoidable. That's your MOS capacitance that we've been talking about. But then there's two capacitances at the end, which are so-called overlap capacitances between the gate and the source, COS, and between gate and drain, COD, okay? Now the COD is particularly problematic because if I look at an equivalent circuit of a MOSFET, okay, that's my input, that's my output, okay? So the COD corresponds to a feedback capacitance between the output terminal and the input terminal, okay? And that's, of course, the source, which is grounded. So that's source, drain, that's my gate, okay? You may have seen this in E438 or some of these other circuit courses, okay? So this feedback capacitance is known as the Miller overlap capacitance, okay? And if you remember your circuit classes, such as 438 or even in 302, you'll see that's very bad because that is a negative feedback capacitance, which hurts your high frequency performance, okay? The reason it's a negative feedback capacitance is the impedance of a capacitor Z. I don't want Z to be confused with the width of the transistor. Let's call it impedance of the capacitor is given by 1 over J omega C. So because of this J term, there'll be a phase shift between this node and this node, and that then causes a negative feedback capacitance, okay? The bottom line is you want this capacitance to be as small as possible, which means you want this overlap between the gate and the drain to be as small as possible, okay? However, you do need some overlap because if you ended up with a gate electrode, which was like this, say, okay? It didn't go all the way across the channel between the source and the drain. What happens then is, in these non-overlap regions, the gate cannot really invert the channel very well, right? So if you draw the potential profile, you'll end up getting additional potential barriers that the gate cannot control very well. And what do you think the impact would be on the transistor performance? So if I had a very short gate that didn't extend all the way between the source to the drain junction, and I plot the potential profile along the channel, you get these bits at the end, this non-overlap region, where you can't reduce the potential barrier in the channel by the gate. And the question for you is, do you think that would hurt the transistor performance? Anybody? If you want to answer, you have to unmute yourself. Do you think that drain current would go up or go down? I hope you guys can hear me. Can you hear me?
Will it go down?
Yeah, it'll go down. Yes, it'll go down because, basically the VT essentially is very high, right? Because now you're depending on fringing fields from the gate turning the transistor on. So you cannot afford to have any underlap. This is called an underlap situation, okay? So you want some overlap, but not too much, because that would then increase the Miller capacitance. So the question is, how do you get to have your cake and eat it too? Let's discuss that, okay? So that brings me to the final part of the discussion of MOSFETs. And I'll illustrate the technology of making MOSFETs by talking about Cmos. Cmos stands for complementary metal oxide semiconductor transistors. Complementary in the sense that you will always have an N-channel device working hand in hand with a P-channel device, illustrated over here for an inverter, okay? So an inverter is the simplest Boolean logic gate that you should have seen in earlier classes. And it's called an inverter because if the input is high, the output will be low, and vice versa. If the input is low voltage, the output will be high. Let's see how that works out, okay? So if my input is high, you see that the output goes low and vice versa. Okay, that's why it's called an inverter. Now, for these NMOS devices, the VT will be generally made slightly positive, okay? Just to make our life simple, let's assume the VT of this is plus 1 volt. Typically, it's more like 0.6, 0.7, but well, the VT for the PMOS will be slightly negative. Let's say it's minus 1 volt, okay? And suppose it's a 5 volt chip. So the VDD power supply is 5 volts, and the source, of course, of the NMOS is grounded, okay? So now, if my input voltage was increased to 5 volts, I'm looking at a digital circuit. Let's see if the NMOS and the PMOS will be on or off, right? So if my input was 5 volts, that's more positive than the threshold voltage of the NMOS. Remember, VG minus VT determines how much gate overdrive I have. I form an inversion region, and that means this node is connected to ground, okay? How about the PMOS? Is that going to be turned on or off? Well, you have to see what the gate to source voltage is and compare that with the threshold voltage, right? In the case of PMOS, you want the gate to source voltage to be more negative than the VT over here, right? Because for PMOS, the gate has to be negative to attract holes in the channel, right? Now, what is the gate to source voltage if I hold the input at 5 volts? For the NMOS, that was 5 volts minus 0. You always measure all your voltages with respect to the source. For the PMOS, it's a little bit trickier, okay? So the PMOS, it's really the source that is connected to VDD, all right? I call that the source because that's a voltage that does not change during circuit operation. The other terminal, the voltage changes between 0 and 5 volts during digital logic, okay? So that's what I'm adjusting, and that is the drain. While this terminal is always connected to a DC fixed voltage, in this case, say 5 volts, and that's considered to be the source of the PMOS. So the source voltage is the one that never changes during circuit operation, okay? So that's the case. When the input is 5 volts, the gate voltage of the PMOS is 5 volts minus 5 volts, or 0. You with me? The gate voltage of the NMOS is 5 volts minus 0 plus 5 volts, but that of the PMOS is 5 minus 5, or 0. Now, 0 is not more negative than minus 1 volt. Therefore, the PMOS will be turned off, while the NMOS will be turned on. So that means that when the input is high, 5 volts, this output node is basically connected to ground, output would be low, okay, as shown over here. Conversely, when the input goes low, suppose the input is at 5 volts, that this scenario, let's see what happens. When the input is low, what is the gate voltage of the NMOS? Well, 0 minus 0 or 0 volts. It's not more positive than the 1 volt threshold voltage. Therefore, now my NMOS will be turned off. How about for the PMOS? Now you might think that if the input is 0, the gate voltage of the PMOS should also be 0. Well, not so, because remember the source of the PMOS is held at plus 5 volts. So the gate voltage is 0 minus 5 volts. Or now the PMOS gate voltage is minus 5 volts, which is more negative than the minus 1 volt VT. Therefore, I attract holes. Therefore, this is on now. Okay. If this is on, the VDD appears at output. So now my output will be 5 volt. Okay. So the punchline is when the input is low, the output goes high, and the input goes high, the output goes low. That's why it's called an inverter. Now, this is the simplest possible logic gate. In actual circuits, you'll have more complicated gates like NAND gates, NOR gates, which I'm not going to get into. If you're interested, that's discussed in chapter 9 of the textbook, okay? But in this class, we may not be responsible for this. Because from a technology or device physics point of view, the inverter captures all the essential physics, okay? Now, let's see how you might make such an inverter on a silicon wafer. Now, if I'm going to make both an NMOS device and the PMOS device on the same piece of silicon, I immediately face a problem. Okay, why? Well, we've seen that for N-channel devices shown on the right-hand side, that's my NMOS device, I have N plus source drains that are typically made in a P-type substrate, right? If I'm going to have enhancement mode devices with a positive threshold voltage. Conversely, P-channel devices shown on the left with P plus source drains typically have to be made in an N-type substrate, right? So that the VT of this can be suitably negative, all right? Now, obviously, I can't have both. I mean, I got to choose, right? It's got to be either a P-type substrate or an N-type substrate, right? So how do I get both types of substrate on one physical substrate, all right? So generally what's done in industry, you go with a P plus substrate, okay? P plus meaning very highly doped, okay? Doped at levels of 10 to the 20 per centimeter cubed, doped with boron, okay? The reason you want it very, very highly doped is because that gives you a very good electrical ground plane. So you can ground the substrate and it gives you a very good reference potential for your chips, okay? But you can't afford to make transistors in such a highly doped substrate because then the VTs will be very positive in the case of NMOS or very negative or very, basically the threshold voltages would be, you cannot control them, right? It would be very, very, very high for the NMOS that you can never turn on. And the PMOS devices, if you made it directly on the P plus, would always be turned on. You can never turn them off, okay? That's why you're forced to make a lightly doped layer on top, which is called an epitaxial layer, okay? I'm not going to go into the physics of that. The way you make these epitaxial thin films was discussed in section 5.1 in chapter 5. And it's also discussed in the Silicon Run video that hopefully you got a chance to look at, okay? Basically, you throw in gases containing silicon at high temperature, and you grow these planes of silicon layer by layer using the underlying substrate as a seed, okay? After you do that, I have to make my billions of transistors on this piece of silicon, right? Maybe an inch by an inch, right? So you have to make sure that adjacent transistors are suitably electrically isolated. And essentially the way you get that is by growing a very, very thick oxide in these isolation regions, okay? Now, I'm not going to go into the details of how that is done. In this cartoon view, you use a technique called local oxidation of silicon, where you locally grow a thick oxide by reacting silicon with oxygen to form SiO2, and you protect these regions where the transistors are made, which are called active regions, by having a silicon nitride protective coat that is then removed before you start making the transistors. All of this, by the way, if you're interested in the details, is given in chapter 9 of the textbook, where we talk about integrated circuits. in this class, you'll not be responsible for those details, okay? Then you make the PMOS and the NMOS in these regions, which are called active regions, as opposed to this part in the middle, which is called an isolation region, because that creates electrical isolation, okay? The active region is where the transistors are. That's where the electrical activity of your circuits are, okay? Okay, so now let's focus on how to make one of these transistors, okay? Well, the first thing, like I said, is you have to make these selective regions, which are N and P type substrates, okay? These are called wells. So these are localized substrates, so that you have N-type region for the PMOS and vice versa, okay? So this is done by having a mask, as shown over here, doing an implant of an N-type donor, such as phosphorus or arsenic, on the right-hand side, okay? Then you form a protective oxide. You then do a P-type implant on the left-hand side, okay? There's a lot of technology in this that I don't have time to get into. Then you form protective layers of silicon nitride, which prevents thermal oxidation. That's this low-cost isolation that I mentioned, okay? You grow a very, very thick oxide here. Here, these are what will isolate this transistor from neighboring transistors, this transistor from neighboring transistors, okay? Then you have to start making the transistors themselves. And the first step there is to form this very, very thin gate oxide, which in the past would be grown thermally by growing a thermal SiO2 by flowing in oxygen and reacting that with silicon, okay? But remember, we said that in a MOSFET, you want this oxide under the gate to be as thin as possible so that Ci is as high as possible so that you can get a high drain current. But the problem there is, if you make the oxide very, very thin, you start encountering a problem. Who remembers what that is?
Leakage, tunneling.
Leakage. Yes, leakage due to quantum mechanical tunneling. Very good. Okay. So because of that, these days, instead of thermal oxide, you'll actually deposit a high K dielectric by techniques such as atomic layer deposition, which is a layer by layer deposition technique. That once again, I don't want to get into. The details are given in chapter 9. Or if you're really interested, I teach a follow-up course, E440, where you talk about the fabrication details, okay? After that, you then deposit the gate electrode. In the past, that would be made up of a highly doped polysilicon layer, where the high doped polysilicon layer basically looked like a metal electrode. But these days, with high K, people actually now make metal electrodes that have to be patterned using photolithography and etched to form these electrodes with hopefully vertical sidewalls. The vertical sidewalls are very important, okay? The reason you have these vertical sidewalls is that is then used to do a self-aligned implant of the source drains. Okay, let's see if I have the terminology over here. This is called a self-aligned implant of source drain. What does that term mean? Okay, so what you have to do is, after I've made my gate electrode, you then ion implant your source drain dopants. In this case, a donor by making an NMOS device, okay? So these will be implants of, say, phosphorus or arsenic, which are typical donors, okay? In ion implantation, as we discussed in chapter 5 very briefly, you create ions of the species somehow, accelerate them to very, very high energies, depending on how deep you want them to go into the substrate, and you slam these ions, say phosphorus ions or arsenic ions, into the wafer, okay? By having this pattern gate, you prevent these ions from entering the channel region over here, okay? So notice the ions go in only at the edges of the gate. So that's what I mean by this term self-aligned implant, okay? So you're not doing a separate photolithographic mask step. You're cleverly using the structure on the chip itself to do the source drain implants, okay? Now that's important because by doing so, you guarantee that you have some overlap between the gate electrode and the source drains, okay? Otherwise, remember we said that you may have this underlap problem that I mentioned, right? Where the gate doesn't extend all the way along the channel, right? Because that would then give rise to these potential energy bumps that you don't want, okay? But at the same time, you don't want too much of an overlap because that increases your Miller feedback capacitance. That is also bad, right? So you want some overlap, but minimum overlap. And you achieve that by doing this self-aligned implant where I'm using the gate electrode itself to block the source drain implant in the channel and allowing them only at the edges of the gate, okay? Now that source drain implant is actually done in 2 steps, okay? The first part is known as a lightly doped source drain implant, or LDD, okay? I wanted to pay attention to this discussion because 99% of transistors that you have in your chips today are basically made by some variation of this technique, okay? Very, very important, okay? And normally in final exams, I ask you to reproduce this because, normally it'll be a closed book exam, but like I told you, this exam is going to be open book. But I'll probably try to find a way of testing you on this, okay? Which won't be simply, repeating what's in these figures, but some variation of that. So you want to study this very, very carefully because, like I said, most chips are made by some variation of this technique, okay? So you make this so-called lightly doped source drain implant. As the name implies, the doping level is modest, of the order of maybe 10 to the 18 per centimeter cube, okay? And you make these junctions as shallow as possible. Why? That's to reduce your short channel effects that I've been discussing, things like dibble or chart sharing, because as I make the channel length shallower and shallower, as I make L smaller, you want these other vertical dimensions to be also reduced, such as source drain junction depths, oxide thicknesses, etc., etc. Remember that? So that's a scaling law, okay? Scaling principle that I mentioned. As you reduce channel length, you reduce all the other dimensions of the transistor in concert with that, including your source drain junction depths, okay? And that's what you do in an LDD, all right? The reason you have a low doping is to minimize your hot electron effects, okay? What is a hot electron effect? Remember we said that when you inject an electron from the source, they can gain kinetic energy in the pinch-off region, and they can become highly energetic, and some of those electrons can be injected into the gate oxide, increase the drain current. You don't want that, right? So to minimize hot electron effect, you basically want to minimize the electric field in this direction. How do you do that? Well, this is a PN junction, right? So that's a P-type channel, and that's an N-type source drain. And you have this peak electric field at the junction, as in a reverse bias PN junction. How do I reduce that peak electric field? Well, if you go back to your PN junction theory, you'll see that if you reduce the doping on either side of a PN junction, that causes the depletion region to expand, and your peak electric field goes down. And that's what I do by having a lightly doped source drain that is self-aligned with respect to the gate edges, okay? So the self-alignment minimizes your minimum overlap capacitance, the Miller overlap capacitance between the gate and the drain. So notice, there's a lot of complicated interrelated things which go into the design of transistors, okay? That's why I'd probably figure out a way to test you on this, okay? Which won't be just repeating what's on the slide, so you really have to understand every aspect of it, okay? We are not done though, okay? If I just had this LDD region, which is lightly doped and very, very shallow, what do you think would happen to the series resistance, RS and RD? Do you think that would be high or low? Well, if I have low doping and very, very thin regions, your source drain resistances would be very, very high. RSD would be very high. Is that good or bad? Well, I just said it's a bad thing, because then any drain voltage that you apply and there's a drain current flowing, you'd waste some voltage, ID times RSD, across this RS and RD regions over here, right? So you want low RSD to minimize this voltage drop, right? So that brings us to the next step, which is these deep, highly doped source drain regions, which are called N plus or P plus in the case of Cmos source drains, okay? Now these you want to offset from these LDD regions. The LDD regions are shown in the slightly shaded regions, while the heavier doped, deeper source drains, which are used to minimize your RSD, are shown in these dark regions, okay? So to do that, what you first do is, after I've made the LDD implants, you deposit an oxide shown in blue uniformly over the whole structure by a technique called chemical vapor deposition, which is conformal. Conformal meaning it conforms to the topography. And then using a plasma-based etch called reactive ion etching, you etch basically in the vertical direction, and it doesn't etch much laterally. Now, if I etch vertically, and I just time the etch to remove these layers, this blue oxide region on these flat surfaces. Notice what happens at the corners. At these corners of the gate, although the oxide thickness was actually uniform, in the vertical dimension, it kind of looks thicker, right? So if I time the edge just right, I'll be left with the so-called sidewall spacers, okay? And that is then used as a second self-aligned implant mask to do these N+ or P+ source strains, okay? So notice I'm doing things very cleverly by making use of the structure itself, okay? So by doing so, you can reduce RSD. Now you reduce RSD even further by forming what is called a silicide, which is shown on the right-hand side. Now, what is a silicide? Well, a silicide involves deposition of a metal such as titanium and reacting that with silicon from the substrate to form an alloy of titanium and silicon called titanium disilicide, okay? So for this, you have to deposit titanium by evaporation or some other technique, and you heat it up so that the titanium reacts with 2 atoms of silicon where it meets the silicon, okay? And it does that in the source and the drain region. On top of the gate, if it was polysilicon, it will form a silicide there also, but if it's a metal gate, it's kind of immaterial. The important point is on the source and the drain regions, okay? Now you want to make sure that it only forms a silicide on the source drain and maybe on top of the gate, but not on the side walls, which are shown in blue, which are made up of oxide, okay? Luckily, the oxide prevents the formation of this titanium disilicide. It leaves it as titanium, which can be etched away selectively, okay? Otherwise, all your source, drains, and gates will be shorted together, okay? And then you're done, okay? So after that, you deposit another oxide. This is to isolate your interconnects from your transistors. You etch contact holes as shown over here. Then you deposit your metal, such as aluminum or these days, copper, okay? You pattern and etch it, and you interconnect your circuits as shown, for example, in this inverter, okay? So the metal is shown by this dark black regions, connecting the NMOS source to the ground, the PMOS source to power supply, the gates, the drain of the NMOS and the PMOS are tied together. That's this connection over here, and so on and so forth, okay? In a practical circuit, of course, these days, you won't have just a single layer of interconnect, but many layers are shown in the next slide. I'm going to skip this one because I've kind of covered this in a different context called the FinFET transistor, which is another way of making so-called silicon and insulators. Very interesting device physics that we don't have time to get into. The essential idea here is when you make your transistors, if you think about it, most of the silicon wafer has no electrical functionality, okay? A silicon wafer is going to be of the order of maybe 700 microns thick, while all your transistors are made in the top maybe 1 micron or so, okay? So the analogy that I use is, it's as if I build a skyscraper and I only allow people to live in the penthouse apartments, right? So the rest of the silicon wafer has no electrical functionality. It's just mechanical support for your transistors, which are made in the top, 1% or so of your silicon wafer, okay? It's kind of a waste if you think about it. So that's kind of the philosophy behind silicon and insulators. So you don't make your transistors in a thick bulk silicon wafer, but in a very, very thin layer of silicon, which is maybe 0.1 microns thick. And then you have an oxide isolating it from the substrate, okay? And that turns out to improve your short channel behavior and many other parameters that I don't have time to get into. So I want to wrap up by talking about parasitic capacitances in an IC. So here I'm looking at a cross-section of a transistor. So we've been focusing on the transistor so far. That's your isolation region. You may have another transistor over here. And then you connect them up by metal electrodes, as I said, okay, depending on the circuits. Now, what you find is in a typical chip today, if you were to show the cross-section, you don't have a single layer of metal interconnects. You have multiple layers of interconnects, okay? In fact, in a modern computer chip, you may have, maybe 20 layers of metal interconnects crisscrossing each other, okay? And the reason you want so many layers of metal interconnects is the same reason why you have overpasses in a city like Austin, right? Because imagine what the traffic flow would be if you didn't allow any overpasses, right? You'd have huge traffic jams. But the same kind of thing is true over here. If I want to route signals from one transistor to the other, and I only had one layer of interconnection, you wouldn't be able to do that. Okay? I would certainly not do that quickly. Okay, so you have these multiple layers of interconnect which across each other and all that, and then you can really route signals very, very effectively. Okay, but when you do that, you have to isolate these metal interconnect layer from an underlying metal interconnection layer, and then above that, I'm not showing it, you'd have other layers of dielectric, higher and higher levels of metal interconnection lines. Okay, and then you join them up as needed by so-called contacts, or you may join, say, this metal with this metal. I'm not showing it over here, but you have other connections that you could make. These contacts are called vias, and so on and so forth. Okay, the point that I'm going to get across is when you have such a highly three-dimensional structure, whether you like it or not, you'll have a whole bunch of capacitances that you deal with, right? Because if you have a metal electrode like this and another metal interconnect line like this, it's like two parallel plate capacitors, right? Where you have a capacitance like this. Similarly, an electrode like this, and maybe a gate electrode, I have a capacitance like this, right? And what is the formula for capacitance? It's given by the dielectric constant epsilon times the area of the capacitor, which is the length times the width. So that's the area of the capacitor, L times W, divided by the thickness of the dielectric D, right? Now you'd want these capacitances to be as low as possible, because if it's very, very high, you end up getting a lot of RC time constants. R comes from the resistance of the interconnect, which is resistivity times length over the cross-sectional area of the interconnect, while C are these overlap capacitances in the structure. Okay. Now you want to minimize both of these, because otherwise your RC time constants of your chips become very, very large. How do you reduce that? Well, for the metal interconnects, you want the resistivity as low as possible. And because of that, people have moved from aluminum, which is pretty low resistivity metal, to even more low resistivity metals such as copper in the most advanced ICs today. All right. The length and these you really can't do very much about, because that depends on the layout of your chip, right? How about for the capacitance? Well, you want to minimize epsilon, the dielectric constant. So unlike the gate dielectric, where you want a high K dielectric, for these oxides over here between the metal interconnects, you want a low K dielectric. And there's a whole bunch of dielectrics that are used, which have a lower dielectric constant than SiO2, which used to be the standard dielectric 20 years ago. Okay. You also want these thicknesses, D, to be as thick as possible. But there's practical limits to that, because if I want to make a very, very thick dielectric, it will take a long time to deposit, and then you have to etch contact holes in that. So there's limits as to how thick you can make D. You want the epsilon to be as low as possible by having low K. You want the resistance to be as low as possible by having as low resistivity of a metal, and that's what you have in a modern IC today. Okay, that concludes our discussion about MOS. Study this chapter very, very carefully, because in the final exam there will be multiple questions on MOS devices, as well as multiple questions on PN junctions, chapter 5. Okay, so the bulk of the questions will be from these two chapters. I want you to study them very, very thoroughly, because they're the most important. Okay, because we'll see in next week, then when you talk about optoelectronic devices, those are basically PN junctions operated in the presence of light. And MOSFETs are very important because, like I said, 99% of your ICs today are made up of MOSFETs. Okay, any questions on MOS? All right, I'll jump to our next transistor structure, which is the bipolar junction transistor. Now, a little bit of history. So it turns out the bipolar transistor was the first transistor that was invented by Bardeen, Brattain, and then Shockley in 1948 or so. And for the next couple of decades, this was the type of transistor which was the dominant technology, because MOSFETs hadn't been made yet. Okay, MOSFETs came a few years later. Okay. Now, BJTs have some advantages, but a lot of disadvantages. The advantage is they tend to be able to conduct a lot more current per unit area, and therefore they're faster than MOSFETs. But because of that, they also consume more power. Okay, and as a result of that, BJTs have been supplanted by Cmos, because as you saw in the Cmos inverter example that I showed you, when you have these Boolean gates, if I have NMOS and PMOS work in tandem, you'll always have either the NMOS on, PMOS off, or vice versa. And as a result, CMOS chips end up consuming very low electrical energy, okay? Low levels of electrical power. And that's what enables you to make, these complex chips with billions of transistors without, draining your battery in your cell phone or burning up your chips, et cetera, okay? So because of that, when I first started out at EP, in '87, I would cover BJTs before MOSFETs, and we would spend a lot of time on BJTs. But because BJTs have not become that important, we've changed the flow, and I'll only cover the most basic fundamentals of BJTs that I'll test you on, and that'll be the discussion today and part of the lecture in the next on Wednesday. But then the advanced aspects of BJTs, I'll sort of go through very, very quickly. I'll not test you on those. I'll tell you what's fair game. So lecture today is fair game, okay? All right, so how does a BJT work? To understand that, let's first look at a p-n junction, okay? And see what the IV characteristics are in the presence of light, photons shining on it, okay? Well, the IV is shown in this curve initially without any extra light shining on it, okay? Of course, even if I'm not shining any extra light from a laser or whatever, remember, even if this diode is sitting on the table, it's not as if nothing is happening, right? Because you can get rid of black body radiation from the surroundings hitting this junction, right? So you'll always have some black body photons, black body radiation, right? And that's what causes this leakage current in reverse bias. While in forward bias, you have an exponential increase of the current. In reverse, you'll get reverse saturation current, and we saw that I equal to some I saturation e to the power QV over KT minus 1, right? So if I reverse bias, this current is simply minus I sat, okay? Which is voltage independent. Now, does anyone remember why this current is voltage independent in reverse bias? Well, when I reverse bias this p-n junction, the band diagram that I got was something like this. That's my P region, that's my N region. And now I have a large voltage drop, which is V naught plus whatever the V reverse bias is, okay? Now, on the P side, although I have majority carrier holes, I still have a few minority carrier electrons in the conduction band, right? Similarly, on the N side, although I have mostly electrons, I have a few minority carrier holes in the valence band, okay? Now, these electrons, minority carrier electrons, can randomly diffuse to the edge of this depletion region, and boom, they're swept across. Similarly for the minority carrier holes, right? And what ends up happening is, as I increase the reverse bias and the electric fields go up, normally you would think that these reverse currents would increase with electric field, but in this particular special case, it doesn't, because it is supply limited. Do you remember the term? So this reverse current doesn't depend on how fast they flow across, but how often they're supplied to the edges of the depletion region, okay? And that supply is limited by this black body radiation. That's what generates your intrinsic carrier concentration, Ni. Hopefully that jogs your memory, right? Okay, so with that background, let's see what would happen if I now shine extra photons on it over and above the black body radiation that you can't do anything about, okay? So this is now a laser maybe shining on this junction, okay? Now next week, when we start talking about optoelectronics, we'll also talk about this, okay? And we'll see what happens with increasing levels of light, okay? We'll see as you shine more and more photons with energy h nu greater than the band gap, you can excite additional electron hole pairs, and those photo-generated carriers will create more supply of carriers, and therefore this leakage current essentially goes up, okay? So here I'm increasing the supply of these minority carriers, hopefully in the vicinity of the junction so that they can be captured via diffusion and then they flow across. This is essentially a preview of optoelectronics that I'll start discussing next week, okay? So this particular example is what is called a photodiode, okay? You're getting a current which is proportional to the light intensity, assuming of course h nu is greater than the band gap, and that's what you have in a photodiode or a photodetector. So that's kind of like a preview of chapter 8, optoelectronics, okay? Now, in this case, in the case of BJTs, I'm using this mainly as a motivator, okay? So the motivation is, I see that the current in a reverse bias PN junction can be controlled by some sort of a hole injector, say, on the N side, or electron injector on the P side, right? A hole injector on the N side by optically generated electron hole pairs, or electron injector on the P side, okay? In this case, let's assume it's a P plus N junction. So I only focus on the N side, right? Because remember, if it was P plus N, the current would be controlled by the doping level on the N side, okay? So I'm looking at a hypothetical hole injector, which is this laser in this case, but let's assume it's some hypothetical hole injector. So if I have a hole injection mechanism, depending on the hole current that I inject, I can control the current in this PN junction. Everybody with me? So this is a reverse bias PN junction, where somehow I have a source of X-ray injection of holes that can be used to control the leakage current of this reverse bias PN junction, which is shown here, but flipped upside down. So now I'm showing this upside, okay? So with increasing hole injection, I can get more and more leakage current of a reverse bias PN junction as shown over here, okay? How do I do that in practice? Well, that's what I do in a bipolar junction transistor operated in the so-called normal active mode of operation, okay? So what I've been talking about so far is a reverse bias PN junction, which is this part on the right-hand side. That's my reverse bias, so-called collector base junction. Now, hopefully I don't know if they talk about BJTs in 302, or some of you have taken 438. I think they talk about BJTs in 438 briefly, right? Is that true? Anybody? It doesn't matter. So here I'm showing this junction reverse bias, and therefore the depletion region is shown to be wider. But then I need a hypothetical hole injector in the vicinity of this reverse bias PN junction, right? Because if I have hole injection in the vicinity of this reverse bias PN junction, that will add to the leakage current of this reverse bias PN junction. I can modulate that current, right? But how do I get that extra hole injection? Well, in the case of a photodetector, that will be by shining a laser in the vicinity of this reverse bias PN junction. We'll talk about that in chapter 8. But instead of that, here, what I do in a BJT is I have another PN junction in close physical proximity that is forward biased, okay? Well, if I have a P plus N junction, that's called the emitter, and I forward bias the thing, I'll inject majority holes from the P to the N side. And in this case, very few back injection of electrons. Now, you might look at the structure and you might think that, yeah, it's perfectly reasonable, right? I get mostly hole current and very little electron current in this junction because I have a higher P-type doping than a lower N-type doping. That sounds reasonable, right? But that is not the case. The reason I have mostly hole current in this forward bias emitter-based junction is not because of a higher P-type doping, but because of a lower N-type doping. Some of you might be going, you might think that, isn't that the same statement backwards? It's not, because I don't know if you remember, I had made a point of this when I discussed PN junction theory. If I ask you, okay, double for me the hole current in this junction, emitter-based junction, what should I do to the structure in terms of doping? How would I double the hole current at this junction, forward bias junction? Anyone remember that?
Half the amount of N-type doping.
Sorry?
Half the amount of N-type doping.
Very good. Excellent. Okay. So if I want to double the hole current, a natural reaction would be I simply double the P plus doping. That would not do a thing at all, because remember, these currents are proportional to Ni squared over Nd, say on the N side. Okay, that's my minority carrier hole current on the N side. Okay, so as you pointed out correctly, if I have the N-type doping on the N side, that doubles Pn, and therefore I get more hole current, right? On the other hand, if I doubled the P plus doping, that does nothing to the hole current, that will simply reduce the back injected electron current by a factor of 2. Okay, that's why in BJT you typically have a highly doped emitter, a lower doped base in the middle, and then a low doped collector. You want this collector to be low doped because this junction is reverse bias, and if the doping was very, very high, the breakdown voltage of this reverse bias junction would be low, which you don't want. Okay. So the way a BJT works is you have a forward bias PN junction, which injects holes into a narrow base. It has to be a narrow base. It cannot be a long base. Okay. Where these injected holes from this forward bias junction now appear in the vicinity of this reverse bias PN junction, where these holes are like minority carriers in this N region. These are these holes, and they can be collected by this reverse bias collector base junction. Now, I said that the base has to be very narrow. And the question for you guys is why, and what does narrow mean? Well, to understand that, we can look at the structure between the emitter and the base. That's my P plus emitter, and that's what's called the base. Okay, I'll tell you why in a second why it's called the base. So when Bardeen, Brattain, and Shockley made the first BJT, they took a piece of germanium. They called that the base. Okay, and they put in two contacts corresponding to the emitter and the collector. Okay, so the emitter was used to emit the current on this base of the structure, and then the collector collected the current. So that's the origin of the name base. Okay, but these days, of course, base is not necessarily made that way. You make two PN junctions in close proximity. Okay, so the question was, why do I need to make this base between the emitter junction and the collector junction narrow, and what does that mean? Okay, well, the reason can be understood by looking at the carrier distribution in this forward bias emitter base junction. Okay, so in the P plus emitter, the current is very low. In the base, I get a higher hole current that is dying down exponentially with distance. Remember that? It's e to the power minus x over LP. And my collector is over here. Now, if my base region was very, very long, what's going to happen? These injected carriers will gradually recombine. And if x is several times this diffusion length, it'll all recombine before these injected holes reach the reverse bias collector. Would that then act as a hole injector that you need in this BJT? Obviously not, right? So you want these injected holes to be able to reach the reverse bias collector base junction, meaning that the base has to be narrow. But narrow compared to what? What is my metric of narrowness? Anybody?
Maybe the depletion region in the collector side of the junction.
No. Narrow compared to the diffusion length. LP is the rate at which it decays by recombination, right? So you don't want it to decay all the way. So you want this base to be short compared to the diffusion length. In other words, you want the collector junction to be so close that these carriers basically go down linearly with distance in the narrow base. Okay. What you mentioned is important for another purpose that I'll discuss on Wednesday. Okay. That's like your Dibble equivalent in a BJT. But the narrow base, the physical length has to be narrow compared to the diffusion length. Okay. Okay, this next slide is very, very important. It essentially captures all the physics of a BJT. Okay, the rest is just math. Okay, so I want you to pay attention to this. Okay, so I'm illustrating this once again for a PNP bipolar transistor. PNP bipolar transistor. Okay, with a P plus emitter, lower doped N-type base, and a P-type collector. Okay, where this junction is going to be reverse biased, and this junction is going to be forward biased, typically. Okay, not necessarily always, but this is the usual mode, which is known as your normal active mode of operation. Okay, so for this junction will be forward biased by having a positive voltage over here with respect to this, and this will be reverse biased, as shown for a PNP device. Okay, now you can of course also make it out of NPN. Okay, and in fact this is more common because instead of whole flow, if I had a BJT based on electron flow, that has a better performance. Why? Well, because electron mobilities are higher than hole mobilities, okay? But it's nice to study the physics in the case of PNPs, because I've noticed that with electrons, because the current direction is opposite to the particle flow, sometimes students can get confused. It's nice in the case of holes, you have the particle flow and the currents in the same direction. And anyway, the physics for NPN is similar, okay? All right, so let's see what happens. So here, in this cartoon view, I'm kind of indicating the magnitudes of the currents by how fat these arrows are, okay? So as you can see, because this emitter-based junction is forward biased, I have mostly hole current flowing across this junction and very little electron current flowing backwards. Once again, not because I have a higher emitter doping P+, but because I have a lower N-type doping in the base, right? So that's what I said in the previous class, okay? Once I inject the holes, they die down exponentially with distance, and it would die down if this width of the base was long compared to the diffusion length. You don't want that. You want the base width to be much, much narrower than the diffusion length, so that essentially the carrier concentration will essentially go down linearly with distance to 0. Why will it go down to 0? That's because this junction is reverse biased, so the carriers are swept right across, and you pull the carrier concentration down to 0. And what it means is, this exponential profile of the injected hole distribution, if I force it to go to 0 at this base collector junction, essentially make it look more or less linear, okay? And that's what you have in a good BJT, as we'll see. All right? Now, unfortunately, what happens is, as you inject these holes, not every hole survives the journey, even if the base is made very narrow. Some of the holes would recombine with electrons, and that is this recombination current. So these injected minority carrier holes are recombining with the majority carrier electrons, as shown over here, okay? So that's recombination in the base. That's one component of this current at the base, IB. The second component of the IB is this back injection of electrons into the forward biased emitter, okay? That's component 5, while component 4 is the recombination losses in the base. So these are the two components which determine your base current. Now we'll see in a couple of slides, in a modern transistor, this is going to be your input terminal, and you want this current to be as small as possible, while the collector is your output terminal. You want this current, IC, to be as large as possible, because then you get a so-called large gain beta. This is called your common emitter gain, which is the output current, collector current, over the input base current. Okay, you want this to be as high as possible, which means you want this to be as low as possible, IC to be as high as possible, okay? Now, on top of that, you also have reverse leakage currents, because this collector-based junction is reverse biased. So that's your regular PN junction diode leakage in the absence of this hole injector that I've talked about, okay? Now, normally in a well-designed transistor with good PN junctions, hopefully these leakage currents are going to be very, very small. So for all practical purposes, we'll be ignoring these, okay? And focus on the dominant current component shown by these big fat arrows over here. All right? So let's summarize what I just said. So this emitter-based junction in the so-called normal active mode of operation is forward biased. You mostly inject holes. Hopefully the vast majority of the holes survive the journey by diffusion across this narrow base and are collected as collector current IC. So I inject a hole current at this junction, which I call IEP. So IEP is just the whole component of the current at this junction. But that's not the total component. You also have a back injection, which gives rise to IEN, okay? But notice, although the electrons are flowing backwards, because the whole electron current vector points opposite to that, this current adds to this current. So for the total emitter current IE is a sum total of your IEP plus IEN, because although the electrons are flowing to the left, the current is pointing to the right, right? Of the injected holes, IEP at this junction, only a certain fraction appear at this collector junction, and that fraction is called your base transport factor. So IEC, so IC will be the so-called base transport factor B times IEP, as shown in the next slide, okay? Don't confuse this B, base transfer factor, with the common emitter current gain beta. So this is a Greek symbol beta. Okay. Everybody okay with this? I'll keep coming back to this figure even next week, even on Wednesday, because this is such an important one in terms of the physics. Okay. All right. Now, in this geometry, this is the so-called common base configuration. Okay, it's kind of like this geometry over here. Okay, where you consider the base to be common between the input emitter in this case and the output collector. That's called the common base mode. Okay, turns out that we'll discuss in the next class. That's not a very desirable mode, because in this mode, although you can get voltage gain, you cannot get current gain, because you can clearly see that the output current IC is going to be a fraction less than 1 of the input IE if I operated the thing in this so-called common base mode. Okay, so I can get voltage gain, but I don't get current gain. Okay, however, you still can get power gain, because power gain is the product of the voltage gain and the current gain. So you still get power gain, but you don't get both voltage and current gain. On the other hand, if you operate a BJT in the so-called common emitter mode, as shown in this figure over here, that's called the common emitter configuration, you can get both voltage and current gain, and of course also power gain. Okay, an active device, by the way, remember, is one which has power gain. Okay, the change of power at the output is more than the change of power at the input. Okay, so input power has to be less than the output power. Okay, that's a hallmark of an active device like a transistor, power gain. Okay, so what do I have in the common emitter configuration? Well, as the name implies, here the input is between the base and the emitter. That's my emitter terminal. And the output is between the collector and the emitter. So it's the emitter that is common between the input loop and the output loop. Okay, and it turns out in this configuration, you can get both voltage and current gain. Okay, I'll go over this again in the next class, but let me give you the preview. Okay, so going back to the previous figure, I said that the collector current IC is equal to your base transport factor B times IEP. Okay, so IC over here is only a fraction less than 1 than IEP that I inject. Okay, why is that less than 1? That's because some of it ends up recombining in the base, recombines with the electrons in the n-type base. Okay, so therefore IEP can never be equal to IC can never be equal to IEP. It'll be slightly less than IEP, maybe 99% or so of IEP. Okay. The second important parameter is called the emitter injection efficiency, and that's the ratio of IEP over IEP plus IEN. What is that? Well, IEP is a good current, right? That's this forward injected whole current, which can contribute to the output collector current, right? On the other hand, IEN is useless current, right? Because that's back injected electrons. And obviously there's no hope of this current contributing to the output collector current. So I call that IEN to be a bad current, right? What is the total emitter current? Well, it's IEP plus IEN. But the good part of the emitter current is only IEP. So that's why I define the so-called emitter injection efficiency as a ratio of this good current, IEP, which can contribute to the output IC over the total emitter current IEP plus the back injected electron part, right? So you want this number to be as close to 1 by minimizing IEN. You also want this to be as close to 1, meaning that most of the injected whole current must survive the journey across the narrow base and appear as collector current. Now, neither of those will be 1. Both of these will be close to 1, maybe 0.99, maybe 0.98. These are typical numbers, okay? Okay, now, one then defines 2 gain parameters. Alpha, this is called your common base gain, which is defined as IC divided by IE. So that's the mode like this, where if this was the input, that's my input current IE, and that's my IC, okay? The ratio of those currents is called alpha. Instead, You generally operate the thing in the common emitter mode, where you have a current gain beta, as I mentioned, with output current is IC, but the input current is not IE, but IB. That's my input current over here, okay? And simple algebra shows that ratio can be very, very large, okay, several hundred. And if you go to the math, that works out to alpha over 1 minus alpha, where alpha itself is very, very close to 1. Alpha turns out to be the product of the base transport factor B times gamma, where both of those, as I said, are numbers generally close to 1. Therefore, alpha is also will be a number close to 1. Therefore, beta, which works out to alpha over 1 minus alpha, suppose alpha was 0.97, right? Then 1 minus alpha would be 0.03, right? And you can see that this ratio would be very, very large, right? Beta can be very, very large. I'm going to go over this again because I'm rushing now, okay? This is actually very straightforward algebra. So from these definitions of the base transfer factor and emitter injection efficiency, you can then come up with the ratio of IC over IE, which is alpha. That simply works out to B times gamma. And then IC over IB, which is my definition of beta, works out to this, which works out to alpha over 1 minus alpha, or B times gamma over 1 minus B times gamma. I'd like you to reproduce this algebra. It's algebra 101, very straightforward, okay? So that on Wednesday, when we start off with this slide, it'll make sense. All right, see you on Wednesday. Any questions? All right, thank you.